Students, today we are solving the CMI 2023 question paper, and we are in question number 2. So suppose that this is given, and rhombus and EF and a triangle we see. So what we can talk about the separate type of triangles over here. The first statement, since ABCD is a rhombus inscribed into this, so with point A on the side of this ED, the diagonals AC and BD intersect at G. Okay, so this creates two triangles EGD and DFB, which is similar by AA angle similarity criteria, and as they share the angle G with an equal alternate interior angle between the parallel lines. So this is a true statement. Next is, it must be true as AC by BD. Okay, this is in a rhombus the diagonals bisect each other, so therefore these two represents the ratios by which the diagonals are bisecting the triangle. So this is also true. GCD cannot be similar to AEB. So GCD and AEB is similar by the angle. So they are similar by the angle similarity, as they share the same angle with this. So this is false. And the last but not the least, for any of the given this thing rhombus. So the statement in this statement is false actually. While it is possible to construct a rhombus inscribed in a rectangle in some cases, but it's not always possible for a given rectangle. So the condition of the rhombus to be inscribed in a rectangle is that diagonals of the rhombus must be intersect the rectangle. Okay, diagonal issue. So if the rectangle is too elongated, maybe has the largest aspect ratio, then like this is the aspect ratio. So the diagonals of the inscribed in it may not intersect each inside this rectangle. Okay, so this small rectangle, this is scope, but here in this case, well, it's very uncool to draw. Okay, so they're making it impossible to construct a described rhombus here as well, so it's not look like a rhombus. So this 8th statement is as false. Next we proceed to 9 and question number 3, which question about the complex numbers. The complex number lies in the third quadrant. Okay, e to the power 3 into I actually equal to e to the power 3i. So cos 3 plus I sin 3. So minus 0.98 plus I into 0.14. So since cos 3 is negative, this is negative and it's positive. The point represents lies on the second quadrant of the complex, not on the third quadrant. So it's the second quadrant, false. Next is z square equal to, so let's take z square equal to rz. R is real one, so considering any explanation to this part of a given structure, for example, we can take the modulus value separately. So we can take it like a mod of z1 minus mod of z2 equal to mod of z1 minus r mod of z1. So z1 we can take common, and 1 minus mod r. So z1 plus z2 mod of z1 plus rz1. Since 1 minus mod equal to 1 minus r mod, so z1 minus z2. So therefore there exist non-zero complex numbers, they can have it in this way. So this statement of 10 is false. The distinct complex numbers z1 and z2 in this at least have 4 solutions. Okay. So this is equidistance from z1 and z2. So like can be simplified as z minus z1 square and equal to z minus z2 square, and this implies that the distance from these two, so therefore the equation has infinitely many solutions, not as 4 solutions only. Okay, so this is also false. Next non-zero complex number z, there are 100 numbers w such that w to the power 2003 equal to z. So k equal to 0, 1, 2, dot, 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 2, 0, 2, 2. If we take, so rewriting e to the power theta and w equal to z to the power 1 by 2023 into e to the power 2k pi 2023 cos theta I sin theta e to the power I theta. 2023 w equal to z to the power z to the power so there are 2023 distinct values of w that satisfies this given structure, so therefore this statement is true.